IDV. This is about digital identity, sub-business of my tech system. In our department called Machine Learning Engineering team, about 5 sub-teams with slightly more than 30 ML engineers. And we are working on the KYC modules. A couple words about KYC. You know, in 2019 and in 2020, COVID forced know your customer systems, remote KYC systems, which allowed to open the banking account remotely. So this guy just lying on a sofa, opening the laptop, making a selfie, making a photo of ID document, and able to open the banking account fully remotely. And there is a huge job behind these simple steps. It includes different modules like background checking and so on in a short latency, but also it includes biometric verification, facial recognition. And facial recognition actually is a technology that is well known. It has very low false match rate, false non-match rate, like false match rate below 0.01%. And this is very well established technology. But the problem is when you are trying to do the facial recognition remotely is to recognize whether this is a real person facing the camera or this is spoofing. We call it spoofing. And the technique that recognizes between the real human and spoofing is called liveness detection. So we are working on liveness detection. Today, I will be talking about liveness detection engine and how we're doing that. This is a real-life example. One guy in Brazil in 2023 opened several banking accounts using this full-size doll. You see, this is real. This is a real picture from Daily Mail news. And this is how it is, how fraudsters deal with remote facial recognition. Let's look what are the other possible ways to spoof remote facial recognition. I'm not aiming to share some secret knowledge on how to do that, but anyway, I need to share a bit about ways of spoofing fraudsters actually do to then share a bit more how we deal with that and how we catch it. On the left part, there is what fraudster does, actually. This is screen presentation, just showing an image on a screen, then moving image closer to the camera, and camera sees this perfect, accurate image. But this is not an image of an actual person. This is a spoofing attack. Another kind of spoofing attack is printed copy, which is widely used as well. Fraudsters simply print the image, the portrait, and then moving closer to the camera, and camera sees again a perfect image of a man looking like a real human in face in front of the camera. And there is a list really during these years. There is a really long list of different types of attacks called presentation attacks, when the fraudster doing nothing with the system actually, just presenting something to the camera. This is 2D mask, this is wax figures, this is silicone, realistic silicone mask. You can buy it on Amazon for $300. Printed cutouts is when a fraudster printing and cutting out the part of the body, including head, and it looks realistically, actually. And the new threat, starting maybe a couple of years, called high-fidelity masks. This is technology almost not available in Europe or in the US. It's available in Asia. In Asia, there are several companies that can do really realistic face masks, 3D masks that fully reproduce the face, the surface of the human face, And one more step is a specific technology that allows to print the texture, the real texture of a face on this mask. So we're dealing with that. And there are two types on how usually fraudsters dealing with attacks. There are two types of attacks in general. The first type on the left part is a so-called presentation attack. Again, fraudster doing nothing with the system, but just presenting something to the camera in accurate manner. And this is called presentation attack. On the right side, there is a more complicated thing, and I need to share this secret as well. If you have two laptops, MacBooks, for example, then there is a way on how you can spoof the other laptop. The source laptop has an image on a screen. It could be a real-life video, stolen video, generated video, any real video with a person. And sync laptop is a laptop that will be breaking. We're simply buying USB video capture for $11 on Amazon, and this USB video capture seen by the operating system as it is a real camera, as it is a real USB camera, but it has no lens. It has an HDMI input, and if you simply connect the USB HDMI adapter to your source laptop, you can reproduce the image from the source laptop, from the screen of the source laptop to the sync laptop. As it's an operating system of the sync laptop will be see this picture as it's coming from a real camera. Because of this is actually the USB camera, the USB video capture. So this is how fraudsters dealing, and there are more numerous ways how they could inject images. And we're dealing with that. More example of injection. The simple one is virtual cameras. I believe many of you already used virtual camera like Manycam or OBS Cam. This is like a software you could install on your laptop, and then you can pass any this software seen as a real camera and operating system, and you can upload the image or video from a storage through this virtual camera and demonstrate it. Someone using it in Zoom calls to imitate they are presenting in front of the camera while long meetings, for example. And more sophisticated injection on the left, where a specific hardware adapter somehow connected to the camera, but this requires very high level of knowledge of the hardware to implement that. The right one is much easier. So this is the description of the task that we have, and this is how we're implementing this is like a very, very general representation of the KYC system. The user installs the mobile application or open the web application on a smartphone, doing the onboarding procedures like making a selfie, like making a photo of the document, and so on. And then this image travels to the KYC server where our algorithm should decide whether this is a real, original image or it is injected or presented to the camera. So from machine learning point of view, for our team, this task looks like a computer vision, classical computer vision task, taking selfie image, providing some procedures, classification, and this is binary problem. Live or spoof is the output of this system. So image on the input and binary decision on the output. And now I'd like to share what is the so-called dual layer approach that we implemented for these purposes. There could be different cases presented to the camera. The good case is a real human making a real selfie to the camera. The bad case is presentation attack. And another bad case is injection of a stolen image or generated image or whatever third-party image of third-party person presented to the system. And in first case, this is just, in second case, this is just a presentation to the camera. In second case, this is somehow injecting an image through device emulator or virtual camera or even JavaScript console or plugin if fraudster dealing with the web application. And we implemented two-level approach that is called detection of presentation artifacts, and second layer called detection of video path artifacts, because on the second layer we're trying to distinguish or recognize the way the signal, the video signal, had in operating system. And this is actually realistically. Okay, let's back to the presentation artifacts and look at these artifacts that could be detected. For example, printed cutouts, you may see it could be detected because of non-realistic edges, right? The 2D mask has non-realistic edges as well. The wax figures, the silicone masks, and high-fidelity masks, more complicated things. If we look at this example, what camera see when presenting an image from the screen. Is it really possible to detect that this is not a real face, but this is a face presented from the screen? Is it feasible, actually? That's a question. And the answer on that is yes, it's possible, because if we look precisely at the, for example, this batch of texture, we can see effect called screen door effect. Screen door effect is the effect when the camera has pixels and the display has, the matrix of camera has pixels and the screen has pixels. So these are two structures that could provide interference. And in frequency domain, it is visible so-called screen door effect. So the neural network can detect that. Another example, is it feasible, again, to, this is more complicated thing, because of here we are not dealing with the screen door effect, we're not dealing with the screen, we're dealing with the printed photo. Printed on a well quality printer, and there is no any screen door effects here. There are almost no any other kind of effects visible by human eye here. So how to deal with that? Actually, if we look at the chromatically diagram, it's called gamut. You may see that real faces or real images has a wider diagram compared to the images printed using a printer, because the printer cannot reproduce the full spectrum of the colors. And if we move to the frequency domain, then we may see that the printed images has reduced space on this diagram. And so the neural network can transfer the image into the frequency domain and make some analysis implicitly and make pretty fine detection of this case. So what we do, we simply gather all the human selfies. We simply gather all the type of presentation attacks like 2D mask, wax figures, silicon masks, and so on and so on. We put the first one, we put the label class 1 for the first ones, class 2 for the second ones, and providing classical training of the neural network used for computer vision tests. And it works, actually. We organize a specific process. We utilize it data collection using Amazon Mechanical Turk and Toloka AI services. They actually have thousands and hundreds of thousands of people who can do a presentation attack for you for some money, for several cents. And we collected million samples using these crowd collection services for training. And then we implemented training within our group and testing and red team, and we even dealt with demographic bias, because when you're dealing with faces, you cannot avoid dealing with demographic bias mitigation. But how to make this technology really, really accurate and first of its class in the world? How to do that? We implemented internal leaderboard. Each of our ML engineer can train a neural network, submit it on the leaderboard, and get some kind of ranking. So we have kind of internal competitions within our team where each author of the neural network, different pipelines, different neural network architectures, different methodologies, different data sets and manipulation with data sets, whatever. But each creator of the neural network can submit it on the leaderboard and see the position of the neural network. And then we select the best neural networks out of this list and do the ensemble of them. And it's very interesting fact, but sometimes some ML engineers outperform the other ML engineers because of different level of skills, experience, and so on. And sometimes on our leaderboard, the first 3 positions are accommodated by the same author, by the same ML engineer. But when we doing an ensemble of neural network, the best ensemble usually consists of neural networks, not from the top of the leaderboard, but from different authors, from different people. And this is actually a very interesting approach. I believe that's because of diversity in pipelines, diversity of approaches allow to make a fusion and ensemble of neural networks from different people better rather than ensemble of neural networks from the same creator. And this is another probably research study, but it's really interesting that diversity in authorship of neural network helped to create pretty great ensemble. And we implemented this feature. We tried to check whether it's working well or not. And you know, NIST is a National Institute of Standards and Technologies here in the US. And they are handling the regular ongoing competition in facial recognition. Probably someone's from you, from this auditorium, knows that well. This is facial recognition vendor test. But starting 2023, due to problems of remote facial recognition, NIST created the first ever challenge devoted to presentation attack detection. And we participated in this challenge, and got the first position here. These are different types of attacks. Some of them are undisclosed. Some of them are disclosed, like flexible silicone masks, photo print replace, and so on. But half of them are not disclosed, unfortunately. And this is the position that we took in each subtask. And if we calculate the overall ranking, then our company will be on the first position. So this is how we dealt with the presentation attack detection. Now moving to the second layer. You remember this diagram where injection attack travels a lot through the operating system before coming to our detector. And this path is specific. The injected image stored somewhere, then probably if it's stored, it's probably compressed. Then it is passed to the virtual camera, for example, and this virtual camera can do the resampling of this image and so on. So it has some transformation with an operation system. Is it really possible to detect between the image captured using a web camera and image injection using a virtual camera? Because they are looking with no difference, actually. But yes, the difference exists. And this picture demonstrates that it will look precisely at the image that has been captured through virtual camera or emulator. It had some artifacts of transformation, resampling, or even compression and decompression, traveling a lot within operating system. And if we implement the detector that can distinguish between the original image and compressed or transformed image, then we can solve the issue and be able to detect if the image has been injected. And we did that the same way. We collected human selfies using crowd collection services, and we did some kind of augmentation. We passed all these human selfies through storage, through JavaScript plugin, through virtual cameras, through device simulators, and other kind of ways of injection through different operating system, and training on the classic neural network that could distinguish between these two classes. And what do we get? This is a result of testing of injection detection accuracy. It is demonstrated in terms of spoofing acceptance rate. The spoofing acceptance rate is the probability that the image, the spoofed image, will be incorrectly recognized as a real one. And we did a lot of tests on different operating systems, Android, Linux, macOS, and so on, in different browsers like Chrome, Firefox, and so on, and in different emulators or virtual cameras. Like this is hardware emulator, this is OBS virtual camera, this is Manycam virtual camera, so a lot of different combinations. This is just a short list of tests that we have internally. It's devoted to virtual cameras only. I believe actually we have much more longer list, but it's not probably useful to put all this stuff on the slide. And this is the spoofing acceptance rate for these combinations of virtual cameras and operating system. Probably the injected image has so significant recompression artifacts that we can detect it with 0 error, while for some of them the acceptance rate higher, but for any of them it's below 0.05%. This is really very, very high accuracy of detection. And moving forward, what about deepfakes? Because I promised to talk about deepfakes. Actually, deepfakes, I believe you know a lot about deepfakes. Deepfakes is something which is fully digital, which has no physical body, instead of like a human who is presented to the camera, or a printed photo, for example, which has physical representation. Deepfakes is fully digital things, so it cannot be easily moved to the system. It should the deepfakes should be injected into the system, so they cannot be presented to the camera, right? They can be injected only. And deepfake actually travels a lot in the operating system. Usually, optionally, it could be stored on a drive and then extracted from a drive through virtual camera and presented to the system by fraudster. And in this case, we can apply the regular deepfake detection as a first layer and detection of video path artifacts as a second layer. And what we see here, I believe you know a lot about deepfakes. And if you look at the open literature, then you may see that the deepfake detection is really, really hard problem. Midjourney and a lot of other companies who are dealing great with deepfakes and have pretty great progress on that. They're changing the deepfake generators from time to time, from month to month. And actually, if you look at the market of deepfake detectors, you may see that deepfake detector usually can have the spoofing acceptance rate like 1% if the deepfake is pretty creepy, and up to 20% if the deepfake is really great and generated with a high resolution. In this case, if we implement the deepfake detection on a regular basis, we cannot detect it with high quality. But if we add the detection of video path artifacts, because we can control the path from the camera, we can have a spoofing acceptance rate of 0.2%. And since the deepfake should pass two detectors, we can apply AND operator, and the spoofing acceptance rate here will be the like roughly multiplication of the first number and second number. So the total spoofing acceptance rate depends on the quality of deepfakes, operating system, and so on. But usually it is under 0.1% in our system because of two-layer approach. That's it. Thank you so much, and thank you for your attention. I'm ready to handle any questions.
Thank you, Konstantin. You all have any questions?
When you were trying to defeat the presentation attacks, did you consider two drivers? How often a normal person blinks during the conversation, and basically you can have like models measuring like what is like how often the fake blinks, and the second one, like how often the normal person is moving the face, so you can measure the coordinates of like nose, ears, and like how often like the head is gonna be tilting like those two factors.
Yeah, you're talking about active liveness, I believe, when the user is asked to move a face or a smartphone.
Face cannot be still, right? So like from time to time, like is it just a snapshot, or you need like a couple of seconds, or like?
We're doing with the 1 second video. 1 second video with no any actions required from the user. So the user can move randomly the head, but can look and still into the camera.
Yeah, it takes time to detect. So like with 2 seconds, yeah, you're probably doing great if you like have those ratios and you still can.
Oh, thank you. Yeah, well, our goal is, we call it zero frictionless. Zero friction or frictionless. When we're not asking user to do something specific to be recognized.
Because if you have like
that's our philosophy.
Time, I mean like 2 minutes, you're gonna detect like anyway, but like in 2 seconds.
Right. Yeah. 1 second actually. 1 second is a very small amount of video frames, and usually there is almost no movements available for that. So the main algorithm dealing with a single image taken from the first second, and some additional algorithms applying for the entire video, but during 1 second only. But it's possible to distinguish some things using just 1 second of video.
Can you still do like the final controlling snapshot? It's like basically the person wouldn't be able to recreate like the second picture, like cut off or something. Right? So like, but you just do one, and that's it. That's what.
Yes.
I'm sorry, what's the name of your product company?
Oh, this is ID R&D. Let me back to the first slide. ID R&D.
Oh, that's the name of your product?
That's the name of the company, and the name of the product is ID Face, ID Live Face, ID Live Face Plus.
And do we have access to this presentation, or is this confidential?
Yeah, sure. I can. We can meet after the. After the.
We can post it to Discord channel.
Do you see any reverse engineering of like basically some of the effects that come from system or storage? Like you could imagine that if you figure out how to reverse engineer that transformation and supply the appropriately changed image, maybe that could kind of be the systems.
You probably mean adversarial attacks. Yeah. It's possible if you have multiple attempts. So our goal is to restrict the number of attempts up to 3, for example. So it's almost impossible to make a good adversarial attack with no attempts, multiple attempts.
Okay, so we've covered how printed pictures have different color schemes and are easier to detect, and how virtual screens are compressing pixels and therefore you can see it as well, and we just covered deepfakes. But what about those silicon masks? How do you detect those?
Oh, that's a great question. I don't know actually how it works, but the neural network knows. Well, yeah, this is really very tricky, but Well, if we look at the real silicon mask, well, this is actually a very great picture of silicon mask. But if you look at the silicon mask that costs $300, that you may see that it has inconsistencies around eyes, because of the human should look through that, and it has the pretty same colored face. So there is almost no difference of the color of the face on different locations of the face, while a real person usually has a different color of different part of the face. So that's my guess how it works.
A follow-up question from me. If there is examples about false positive, and even there's a real person, and the system detects it as a fake, how do you deal with that?
Yeah, that's a great question. I expected some kind of question because I never mentioned this number. But this is a really important number because of high false rejection rate, lower usability, right? But for all of these tables, numbers, the false rejection rate is 2%. We're keeping 2% false rejection rate, so 98% of attempts of real persons will be successful. And this is pretty great number for KYC system.
Yeah, I don't know if I need that. My question is on, PyTorch versus TensorFlow. Is there a clear winner? Do you have a favorite based on all of this?
TensorFlow vs PyTorch.
And PyTorch and TensorFlow, right?
Oh.
Which one do you use?
I think you said you use both, right?
We have different preferences within a company. Usually, half of ML engineers in our team prefers TensorFlow, and another half prefers PyTorch. And we're dealing with mostly TensorFlow because it could be fully implemented on device. Right now, it has TensorFlow Lite implementation, while PyTorch is on its way there.
That's that model that have the highest performance is the mix of TensorFlow and PyTorch.
Yes, but we're using that for challenges usually. We cannot put it, PyTorch in production, unfortunately.
Interesting talk. I have a question about your video path artifacts. You're basically detecting decompression artifacts, right? It's double JPEG compression. Well, that's the exact thing, right? Is it different than that?
Well, it's not. I call it recompression, but actually this is not a recompression only. In this way, if the image is stored in, JPEG format, for example, and then, or if it's a video in MPEG, and then pass it to virtual camera where it is recompressed, then this is recompression. But if it's passed as is to the virtual camera, usually virtual camera doing some transformation from one format to another, resembling. So this is complex transformation of the image within operating system.
So video path is equals decompression detection?
Like that, yes.
And also the second question would be, like, if you remove the storage, device emulator, virtual camera, like this whole thing, and put a deepfake pipeline right now in the middle, there's no storage, right? So it's immediately a person sitting there, they immediately faking and then goes to your, how would that, how the solution improve?
Well, that's a great question. If you could put that, let me look at the diagram here. Okay, if we putting the deepfake as is into the system, then anyway you need to utilize virtual camera or device emulator or something that.
Storage, right? So there's no recompression there. So it's automatically coming out of it.
If there is no storage, there will be a kind of transformation within virtual camera, for example. Or
virtual camera is exactly as the physical camera, right? It's like it will take the sample directly, like it's being fed into the system directly, so it's nothing different than that actually.
Okay, you're trying to spoof our system right now. Yeah. That's a great idea. I would like to say that's a great idea, but actually there are some additional transformations usually. Yeah,
Are you checking the drivers then for virtual camera, or like for physical?
Yes, we have software checks. Yes, we have software checks as well. That's checking The functions available because of function of real camera and virtual camera usually different. The resolution list of the virtual camera and physical camera is different as well. So yeah, there are some kind of software checks additionally. I cannot disclose everything. My colleagues kill me.
About the length of the video, I know you said 1 second, but did you try to use different video length? Maybe half a second will work as good, or maybe 1.5 seconds will work much better.
That's a great question. I have no almost knowledge about that. I believe our guys did some experiments on that and found that 1 second is something most applicable here. But no, I cannot comment that. No, I don't know exact numbers, sorry. Okay.
Thank you.
Thank you.
Right. Thank you, Konstantin. And yeah,
Recording stopped.
thanks everyone for joining us today. That was our ML conversation with that, and stay here for some time. Mel, these are people, and then join us at the bar in half an hour or something, right? Yeah, we'll have a link for the group in. Thank you.
I just need to mention that we have to be out of here by 9, and event at the bar is not sponsored event. But everyone is welcome.